Okay, so I am now into the shell, and I'm just looking at a little example problem for week 2. And this is really important that you know what the higher heating value is and the lower heating value is. I'll just give you a little graphical demonstration of what this is. So if I've got, if I have two things combining, so what I'm going to have, and I'm just going to write CXHY for my hydrocarbon, and then I'm going to write O2, I'll just write NO2 for some number of oxygen atoms. Those two combine, they make heat. If, let's just say you're going to make electricity with this heat. If you have a flow of water coming through, so here's your H2O coming through. It gets hot as it enters this combustion stream. As it comes out, you're going to see steam. And as you know, steam is typically used to spin a turbine and make electricity. Now, a couple different things can happen. One, if you've got your, let's just say you've got your turbine here. If the steam simply leaves, you still have thermal energy exiting the system. But if you recover that steam, you've essentially recaptured that thermal energy. So if this happens, really all you're getting is the lower heating value of the fuel. So remember, energy is, I'll just write it as energy sub C for chemical. Chemical energy is here, turns into thermal energy. If that thermal energy leaves as steam off to the atmosphere, you've captured the so-called lower heating value. If you bring it back into your system, what you're looking at is the higher heating value. So if you're looking for a more efficient means of combustion, you're going to want to use the HHV. Now, this little problem is not even going into that much detail. All it's asking you to do is convert from megajoules per kilogram to BTUs per pound. So I'm not going to write this out, but you can just see at this point it's just a matter of keeping track of units. So 37.2 megajoules per kilogram. We multiply that, so 1 kilogram is 2.2 pounds. The kilograms disappear. We also know that there are 947.81 BTUs per megajoule. You do the algebra, and then you're left with 1,645 BTUs per pound. And so really, and the purpose for doing that is to know that the latent heat of vaporization, and this is 2,257 kilojoules per kilogram, that's basically what you're losing out here. So for every 1 kilogram of steam that leaves the system, you're basically losing that 2257 kilojoules, or 2.257 megajoules. But if you recondense it, bring it back into the system, use it for heating, you're working with the higher heating value. So the problem is just converting that lower heating value from kilojoules per kilogram to BTUs per pound. And the latent heat of vaporization is just the difference. So I'll just write it like this: latent heat of vaporization equals the higher heating value minus the lower heating value. So what I've sort of drawn here in this little graphic, I've just written mathematically. So latent heat of vaporization equals the higher heating value minus the lower heating value. Okay, so that's all I'm going to give you for today. Do take a look. I am going to wrap up the week. I'm going to start the week 3 forum, so we're back on track with that. And if you have questions on the week 2 homework or the week 2 exam, let me know and I'll get back to you via email. So thanks a lot, and I'll see you on Tuesday.